Welcome to this lecture in the ongoing series of lectures in real analysis. Last time we discussed the notion of tangents on, or rather right tangents and left tangents on the graph at a given point on the graph of a function. And today we'll be defining what is meant by differentiability and what is the derivative. So let us quickly recall what we discussed the last time. So first we defined the notion of a right half plane or an open right half plane. So whenever I write right half plane, I mean open right half plane. So right half plane was defined as first we fix a real number x naught, and then this is the notation for it, and it is the set of all those points in the plane such that the x coordinate strictly exceeds x naught. So all the points which are strictly on the right side of this vertical line. Then we define what is meant by a right ray or a left ray. So fix a point in the plane. Then a right ray is a ray starting at this point, which proceeds in sort of like in the right direction rather than in the left direction. It can go downwards or upwards, but it proceeds in the right direction. And the formal expression would be something like, there could be other ways to express this, but this is one way to express a ray starting at x naught comma y naught and proceeding in the right direction with slope m. So we are familiar with the notion of the slope of a line or a ray from high school. It's the rise over run. So you pick 2 points and then you take the ratio of the vertical guy with the horizontal guy. That's what that's what the slope is. All right, so we are just not allowing vertical lines, or rather this definition cannot give you the vertical line or the downwards vertical line, because m cannot be put equal to infinity. That would make no sense. So we just don't care about vertical lines. All right, then we defined epsilon cones about a given ray. So if you fix a ray, let's say it's a right ray, and let's say it has slope m. Now the epsilon cone about this ray is all those lines, or rather sorry, all those right rays starting at this point which have slope strictly between m plus epsilon and m minus epsilon, and that was this region. And yeah, so that's what it was, and we formally can express this by writing c epsilon rho equals x comma theta x minus x naught plus y naught, with the property that this is the case, and the second is that theta doesn't deviate from m too much. This is how we expressed it, and there is another way to express it, and that I will give as an exercise. Okay. So finally we define the most important concept, which is that of a right tangent. So or a left tangent, but I will only recall the definition of right tangent. So what we do is we fix a graph, fix a function. Let's say the graph is like this. We fix a point in the domain, and then we get a point a comma fa. So a right ray starting at this point is called a right tangent to this graph if whenever we make an epsilon cone about this ray with epsilon of our choice, it just needs to be positive, then there is a delta greater than 0 such that the graph of the function above this right delta neighborhood is completely contained in the epsilon cone. So that was the definition, and we discussed it at length, and one should feel that this is indeed capturing the notion of tangent really very clearly. Okay, so that was the definition, and let me give one exercise before we move on. I thought that I had written it, but I have not. Oops, what did I do? Okay, so there will only be one problem. So let x0 comma y0 be a point in R2, and let rho equals x comma m x minus x0 plus y0 in R2 x greater than equal to x0. So this is we have fixed a right ray starting at the point x0 comma y0. Let epsilon greater than 0 show that C epsilon rho is nothing but those points in R2 with x greater than equal to, with x greater than x0, and with the property that y minus y0 upon x minus x0, lack of space, minus m is less than epsilon, and with one extra point. So we also fit that in. So try to understand the meaning of this. This is the slope of, so let me draw a diagram. So I have this point x0 comma y0, and now if you take this into consideration and pick a point x comma y, so it will be somewhere here. It could be below this line also, above this line also. It's just that the x coordinate strictly exceeds x0. So what is this? This is reading simply this ratio, this divided by that. That's precisely what this is, meaning the slope of this ray, and this is saying that the slope is between m plus epsilon and m minus epsilon, strictly between that. So this should intuitively immediately be clear that yes, this is almost almost the epsilon cone as we define it, except that it is missing this point, and so we forcefully put that in because you cannot take the ratio of 0.0. So that's this is a very simple exercise, but I wanted to give this. Okay, so now we get to derivatives. Okay, so again it's the same kind of hypothesis. So let f be a function defined on an interval I okay, and let a in I be not the right boundary point of I. Again, let there be no confusion. I may not have any boundary points, let alone a right boundary point or the right boundary point. But all we are insisting is that this is not the right boundary point. Okay, and what does that mean? Let me also explain that. So that means that there exists delta greater than 0 such that a comma a plus delta is contained in the interval. That's what this means. All right. And here is the definition. So we say f is right differentiable at a if there exists a right tangent at a comma f of a to the graph of f. And again, let there be no confusion. The right tangent, if it exists, is unique, even though the way we've written it suggests that there may be multiple, but we showed that if it exists, it is unique. Okay. So similarly, one can define left differentiability. That I leave to you. Left differentiable. All right. Okay. Now, so we have defined the notion of right differentiable at a point. Now we want to define the notion of differentiable. Or we want to say that a function is differentiable at a point if it is both right and left differentiable. And those two, okay, so I'll get to that. Right, so what do we mean by differentiability of a function? So let a in I be in the interior of I. What does that mean? Let us recall what does that mean. That is, there exists delta greater than 0 such that a minus delta, a plus delta is contained in the interval. Right? So for this kind of point, first we will define differentiability, and then we will look at what is meant by differentiability at non-interior points, meaning at boundary points. So we say f is right differentiable, f is differentiable. Actually, I'm under heavy medication, so I'm not at the top of my game today. F is differentiable at a if f is both, so it's two things. So first is f is both right and left differentiable, and second is that the right and left tangents at a comma fa to the graph of f have the same slope. Which really geometrically it means that the two drawn together form a single line. Let's see an example. So here we have the absolute value function. Now at the origin, at 0, it is both right and left differentiable. The right tangent is this itself and the left tangent is that itself, but together the right and the left tangent, they do not constitute a single line. There's an angle between them. While as we saw in the previous lecture, if I take the x going to x square function, it's sort of like this. Yeah, if I take that function, then the right tangent is this and the left tangent is that, and if you just draw them both together, then you just get one single line, which is the horizontal line in this case. So just the existence of right and left tangents is not enough to say that the function is differentiable. There is one extra condition, that they have the same slope. So we have defined what is meant by differentiability. But this makes sense only at an interior point, because if the point is not an interior point, you can't talk about both right and left derivatives. At a boundary point, you can talk about only one of the derivatives. So, so just to accommodate those points, we will make two separate kind of cases. So if A is a right, or rather the right boundary point of I, then we say that f is differentiable at A. If f is left differentiable at A, because it simply doesn't make sense to talk about the right derivative or right tangent, not derivative, I haven't even defined derivatives. It doesn't make sense to talk about the right tangent at the right boundary point. So for example, let me first highlight. So if suppose my function is defined on this, let's say this kind of closed interval, and the graph of the function is whatever it could be, something like this, let's say. So here I can't talk about right tangent. There is nothing on the right side, so there is no notion of tangents. Right, we define right tangents only for the points which were not right boundary points. So here we can only talk about left tangent, if at all, and that's why differentiability only talks about left, only cares about the left tangent, and hence left differentiability. Okay. So similarly, if A is the left boundary point, of I, then blah blah blah, f is right differentiable. So this blah 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 is this line inserted here. Okay. So these are a bunch of definitions. Nothing, we haven't done any mathematics in some sense. I mean, mathematics is a lot about definitions, but you get what I'm trying to say. My handwriting is also very bad today. Okay, finally, we define the derivative. So let A, okay, so again, so we have a function f from I to R, and A in I is not the right boundary point if one exists. So then the right derivative of f at A, okay, so assume f is right differentiable at A. Assume f is right differentiable at A. And now the right derivative of f at A is defined as the slope of the right tangent. add a comma fa to the graph of f, right? So now we have defined derivative. We have assigned a number finally. It's not just a geometric object associated to the point A, it's now a number associated to the point A. Okay. So yeah, I wanted to say, so the notation, the right, it is denoted by f r prime bracket A. So this r of course refers to right. This r refers to right. This prime is for derivative. This A is the point where you're taking the derivative. Okay, that's the notation. And let me make one more remark. So now if f is a function from I to r, then you get a function f prime r, and just to be, completely safe, let me write interior of I to r, assuming f is right differentiable. So if this is a right differentiable function, then you can define a new function which is defined on the interior of I. You could also include the left boundary point here, but let me just restrict to the interior of I. So this new function takes points in the interior of I and produces real numbers, what is this function? It just consumes a point and produces the right derivative, just takes the slope of the right tangent. So that's your new function. So this is really a function, assuming right differentiability of the parent function, right? Okay. And now finally, for a very important conclusion, this is a theorem or a lemma, whatever you want to call it. So let f be a be a function defined on an interval. YouTube forward button is your friend. And a and I be not the right boundary point. Of I, then if f is right differentiable at A, and f is right continuous at A. So let us see why is that. So we have the point A comma f of A. Let me take more space. We have A comma f of A. And let's say this is your right tangent. Wow, this looks so beautiful. Maybe because it's not proper. So we have the right tangent starting at that point. And we want to show that this is the function is right continuous at the point A. So what do we need to do? To show right continuity, first we will take the right epsilon band. Let me write it here. A comma f of A. So we will take the right epsilon band. You fix an epsilon greater than 0 and take the right epsilon band. So this is epsilon. Let me mention that. And what do we want to show? We want to show that there is a delta greater than 0. There exists delta greater than 0 such that the graph of the function above a comma a plus delta is contained in the right epsilon band. So let me say this is maybe band epsilon a comma fa. So this region is what I am denoting by this B for band. Right, so please make a note of this. Fine, but what we are given is that the function is right differentiable. Okay, so basically you choose your whatever epsilon is already taken, but just take any cone about this right ray. Just take any cone about this right ray. So let's say this is maybe what's a good Greek symbol? Alpha cone. So let me shade it. So this shaded region is the alpha cone about the right ray. C alpha rho. This is rho. Now a little bit of calculation will show you that there is a some, let me call it, I don't know what is a good, there is a beta greater than 0 such that if you take all the points in the cone which have x coordinate less than beta, then all of those points are also contained in the right epsilon band. So here is the statement that I'm making. So there is beta greater than 0 such that the cone, if you take the points in the cone with the property that their y coordinate is at most beta, this is contained in the right epsilon band. This is the way to formally express what I just said. There is some beta greater than 0 such that if you take only those points whose beta coordinate is, sorry, whose y coordinate, oh no, I don't want y coordinate, I want the x coordinate. This is x. Sorry, whose x coordinate is less than beta. So all of these points, and you consider only those points which are in the cone with this additional property, then all of those points are actually contained in the right epsilon band, and that is clear from the picture, and you can actually argue that because you know precisely what this cone is, you know precisely what this band is. So that's not hard to do, it's just a tedious algebraic calculation. Okay, and now since this rho is indeed the right tangent, so by the fact that rho is the right tangent, at a comma f of a to the graph of f, there is delta greater than 0, which we may assume is less than beta, and we may assume that delta is less than beta because you can always cut down delta. Whatever delta you can take the minimum of delta and beta, and there is no problem. There is delta greater than 0 such that the graph of f restricted to a comma a plus delta is contained in C epsilon rho. Okay, but any point here has x coordinate at most beta, or rather strictly less than beta, because the x coordinate here is strictly less than delta, and we have assumed delta is less than beta. So all of these points are in here because of the condition that this is the right tangent. Let's say this is delta and delta is less than beta. So all of these orange points, this orange thing is the graph of the function above a and a plus delta. So all of these points are here in the cone, but since by the choice of beta, all of these points are also in this region where the x coordinate is at most beta. So therefore, by this line, this implies that this is actually contained in the right epsilon band. So please understand this implication. All of these points are here and all of these points are also here. So these points are here because they are in this intersection. So we have this containment, and this is what we wanted to show. This is what we wanted to show. You look at this. This is what is meant by right continuity. And this is the reason why I stressed so much on the geometric definitions. In textbooks, the way this thing is proven is by doing some analytical limit business. They do not in textbooks they do not define right tangents or anything. They just define a certain limiting thing, limit f of x minus f of a upon x minus a, etc. We'll get to that. But then using that limiting definition, some algebraic and some estimates, they ultimately end up showing this. But I think it is much better to see this just as a geometric thing. You can see this. You can see why right differentiability implies right continuity, rather than doing some calculation and figuring it out. It's completely transparent. And also this further shows that actually differentiability is a very strong condition compared to continuity. Here we just took some alpha cone, and that was it. You don't need the existence of, you don't need the full power of the hypothesis of right differentiability. You don't need to know that for each alpha greater than 0, there is some delta greater than 0, such that when you consider the graph of the function above a and a plus delta, it will be lying in this alpha cone. You don't need to know the full, you don't need the truth of it for each alpha greater than 0. Just some alpha greater than 0 is enough, right? So differentiability is a much stronger condition. Okay, so please stay on this proof if you don't get it initially, and that is the way to do mathematics anyway. So if I give a proof and you do not immediately follow it, you should stay on it and figure out what's going on. Especially that there are proofs which I stress. Those ones you should definitely spend time on. So I hope this is clear. There is just the picture is the most important thing, and you should understand it in terms of pictures. Okay, so right differentiability implies right continuity, and similarly one can now say that if f is differentiable, f is some function a in I, if f is differentiable at a, then f is continuous at a. So this I leave to you because it is exactly similar to the previous theorem. So differentiability implies continuity. Right differentiability implies right continuity. Left differentiability implies left continuity. Okay. So I'm done. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.